Hello, linear algebra student. This video is for chapter 1.9, part 1. We're going to talk about linear transformation in more details and different types of linear transformation. That's what this chapter is about. And also a very important theorem that we're going to cover is theorem 10. We know that what is a linear transformation? A linear transformation is to map a vector from R to the n or Rn to Rm. So basically you have a vector which is a weight of x1 to xm. No, x1 to xn. So these are weights, and then you make it, and then like you can change it around whatever method. So it become a b1 to bm. They don't have to be the same matrix. So whatever method, this is the rule. Okay. So what is the criteria? So this is a transformation. The criteria for be a linear transformation would be what? T of u plus v. If you add these two matrices of here together, it's the same as you do it individually. And the second is if you do a transformation of a scalar multiplied by a matrix, it's the same as you multiply it later after transforming it. So this is called linear transformation. And so like what I said before, so it could be like done by the transformation can be done by a matrix, but you can actually have any rule that can do it. But what happened is if it is a linear transformation, it must be the same, or it must be able to represent it as AX. That means no matter what you do, eventually there is a matrix AX that helps you produce the output. So this is very important. So because like you can switch things around, you can, add things together so long as you obey these two. What happened is actually can be done through a matrix A, and we call this a standard matrix. A standard matrix. So this is the term. So if someone say, give me the standard matrix for a transformation, that just means the matrix that can perform the same thing as the rule of the transformation. And actually, theorem 10 actually tells you how to create it. And actually, part of the proof is you do the transformation of E1 up to the transformation of En. So you have n columns. Each one would be used by this ways to do a linear combination of them into a BM. And so all these columns are M row because there's M row, right? So, but N column. So the way we do it is we do them one by one. So what is E1? E1 is like 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0. So each column has only 1, 1 in the corresponding row. Okay, so this is how you make it. And that's how you write it out. For example, I have a transformation that contract. So it's R2 to R2. Okay, contract a R2 to 1/3 of contract a x1 x2 into 1/3 of x1 x2. So the transformation is defined as I have x1 x2, and the results become 1/3 of x1 and then 1/3 of x2. So this is just a rule, right? Rule is times 1/3, but we can actually do a matrix that do the same thing. So what is the matrix? The matrix is how you would do this for E1 and how you would do it for E2, because there's only two column, right? Two column. So how do I do? So what is E1? E1 is 1, 0. So I'm going to do T of 1, 0. 1, 0, why? Because the x1 axis is this, and we call this the x2 axis. So this point is 1, 0, 1, 0, right? So if I am to do 1/3, so 1, 0 will become 1/3 of 1/3 and then 0, right? And what about the other one? 0, 1, it would be E1, right? E2 will be 0, 1. It's actually this vector, right over here, 0, 1. And so 1/3 means it's 0, 1/3. So the standard matrix would be have this a result of 1, 0, which is 1/3, 0. And the second one would be the result of transformation of 0, 1 is 0, 1/3. So this is A. This would do the same thing as contracting x1, x2 into 1/3 of x1, x2. And we can check it. So just try. So say, for example, my input x1, x2 is 3, 3. Okay. 3, 3. What is t of 3, 3? So I'm going to multiply it by 1, 3, 0, 0, 1, 3, and then 3, 3. Remember how to do matrix multiplication? We should row cross, right? So that's 1. The row and then down, so that's also 1. So you can see that it's begin with 3, 3, and now it become 1, 1. It is contracted by 1/3, multiply 1/3. So this is the standard matrix that define the rule. The rule can be defined verbally or whatever, or geometrically, but you can find a matrix for it. Another one, find a standard matrix for rotating the point about the origin through an angle alpha. So this is rotate. Okay, so x1, x2. The rule is rotate through alpha, and this would be what would that be? It would be B1, B2, right? So this is like that. We don't know what it is, but we can geometrically think about it. So let's try T of E1. That means T of 1, 0. So I'm going to draw a picture of 1, 0. I rotate through an angle alpha. So for example, this is alpha. So where would my new x and y be? So this is almost like the unit circle, because the unit circle would have 1, 0 in the beginning, right? So if this is alpha, so like in trigonometry's unit circle, our x is cosine alpha, right? Our y is sine alpha. Just to remember. So this is good. So if I have 1, 0, the answer would be cosine alpha and sine alpha. What about T01? So T01 would be here, right? Oh, well, so if this rotate over here by alpha, that means it's actually totally you're rotating what? So you're rotating 90 degree plus alpha, right? So you can think of it as cosine alpha plus 90 degree and sine alpha plus 90 degree. Cosine alpha plus 90 degree means what? If this is 90 degree, so that means we can simplify this. What would this be? So this is equal to 90, use cofunction. This means sine 90 minus it, right? Because cosine of any theta is equal to sine 90 minus theta. You can also use some difference angle. So if I do 90 minus this one, it will be 90 minus alpha and minus 90. So that would be negative alpha. And that's actually negative sine alpha. And then what about 90 cosine? 90 minus this, so this goes away. But it will be negative alpha. Cosine is an even function, so it's just cosine alpha. So you can see that the new A, not enough space. So A would be equal to, what is the standard matrix? The top would be cosine alpha, sine alpha, and this would be negative sine alpha, cosine alpha. That's how we know the rotation matrix. Example 3, so if I have a transformation that do x1, x2, so what happened is it's called a horizontal shear transformation. E1 is unchanged. So E1 just become E1, but then E2 is going to E2 plus 3E1. So this is a description. The description is E1 become E1, E2 become E2 plus 3E1. So I'm just going to do the matrix. The matrix would be A equal to T of E1 and then T of E2. So what is T of E1? T of E1 is unchanged, so T of 1, 0 is 1, 0, because that's E1. Then we're going to do T of E2. T of E2, which is T of 0, 1, they say that is equal to what? It's equal to E2 itself add 3 times of E1, which is 1, 0. So that means if you add them together, there will be 3, 1. So A itself would be combining T of E1, that is equal to 1, 0, and T of E2, which is 3, 1. And if you multiply X, if you have A multiply X, it would be doing the same transformation that we described above. So that is a very important theorem, Theorem 10. Any linear transformation can be done that way. So if you look at the books, page 74, 75, they will go through the main one. So reflection, they will go through contraction, projection, and all those. So you can actually look at the book and then look at these. These are pre-made standard matrix. Let's do another example. So this is an example that do 2 transformations, one after the other. These transformations are the one that we described earlier, but then it is 2 of them. So we'll construct the standard matrix again. So it goes like this. First step, they have 2 steps. We flag the points through the horizontal x1 axis. We flag first over x1 axis. And the second step is we flag through x equal to y, or x1 equal to x2. Okay, y equal to x, or x2 equal to x1. So that means x1 and x2's coordinate switch. So let's do t of 1, 0. Okay, t of 1, 0, I graph it is like here, right? If I reflect over the x-axis, that is just 1, 0, right? Because you don't reflect anything. And then step 2 would be do this. First step, do this. And then reflect this over x2 and x1. That means x1 and x2 switch. So that means 0, 1. And then we do t 1, 0, e2. This is e1. And it would be this vector. If you are going to reflect this through the horizontal axis, that would become 1, 0 would become, no, this is not 1, 0, it's 0, 1, right? We do 0 and then 1. It will be 0, negative 1, right? And then the second step, so step 1, step 2, so this is step 1, step 2. Step 2 is reflect over x equal to y, that means switch them. Okay, 1, 0. Oh, no, okay, so this is 0, 1. So, and then you switch them around, so it become 1, 0. So the A would become 0, 1. And, oh no, this is a 0, negative 1. 0, -1, because if you reflect it, it becomes 0, -1, right? Reflects down. So negative